Okay, assalamualaikum and good morning. Alright, so in this video I would like to give an example of uh, the measure phase. And of course in Six Sigma, even though we are discussing about measure phase, it will connected to the previous phase, which is the define phase. Right, so the purpose of this video is to show how we can construct the cause and effect diagram, as well as the FMEA. Okay, so from the problem that we studied. Okay, so let's consider an example of problem here. So ABC Enterprise is a machining shop that supplies components to a few manufacturing assemblers. For the past 3 months, the number of complaints from customers has increased about 34%. If the customer satisfaction is not become better, the contract from customer will not be continued for the following fiscal year. The company will suffer to survive if no new contract is obtained. So this is the problem that we consider. Okay, so from the problem, okay, let's us recap a few things in define phase. So we try to conduct a survey to identify the reason for customers unsatisfaction. So we conduct a survey and we plot the result in the Pareto chart. We find out that the main problem that we face is the quality problem. So the most complaint coming from the customers are regarding the quality problem. And beside that, we also have the poor packaging and so on. Right, so in this project, so we will focus on the quality issue. So next, so regarding the quality issue, we also need to go into detail what does the quality issue here referring to. Okay, so again we conduct a survey. So we find out that the surface finish, okay, the surface finish is the largest issue, followed by the dents on the component, okay, burn on the surface, material problem, leftover material, and so on. All right, so we will focus on the surface finish issue. All right, so from there, okay, so we conduct a CTQ drill down to identify what are the quality drivers and also indicators that we can use. Okay, so based on the survey that has been conducted, the main issue is regarding the surface finish. Okay, so we need to interpret the customer's requirement here into the quality drivers. Okay, so what does it mean by the surface finish, good surface finish? So maybe the good surface finish can be defined as the shining of the part, okay, the surface roughness of the part, the aesthetics look, then the dent. Okay, so these are some of the quality drivers and the indicators regarding of each quality drivers. For example, for shining, how we can determine or how we can define the shining part. Okay, so for example, we can define the shining part by using the gloss meter, right? So it must have a certain value. For example, 550 gloss meter or better. So it's this number or this indicator indicate a good shining characteristics of the part. Then we also have the wavelength measurement using spectrometer, okay, less than or equal to 340 nanometer. Okay, so these are the indicators that we can use to define the shining quality. Then in terms of surface roughness, the surface roughness at least 50 micron, for example. Then the skewness or symmetry of the profile about the mean line less than 35 micron. Then the kurtosis measure the sharpness of the surface profile. So these are some of the indicators that can be used to interpret the surface roughness in the measurable indicators. Then for aesthetics, okay, maybe rating 8 out of 10 or above. Then the dent, okay, 0.2 dent per batch. Okay, means that we are processing the parts in a batch of maybe 100 or 50 units, but only 0.2 or 20, 0.2 dents per batch that we identify. Okay, so if the dent is less than this number, means that we have a good dent characteristics. Okay. Right, so next we move to a process map. So we can use the uh, flow chart, okay, to show the overall process. Okay, so it begin with material preparation, casting process, deburring process, turning process, milling process, and so on. Okay, so for the process map, we need to know the input and output, right? So we can use a SIPOC diagram. Okay, so we begin with the casting. So what are the output from the casting? Of course, the casting product. Then the customer will be the deburring department, the following department, and the turning department. Then the material for the casting, the input for the casting will be material, mold, furnace, flux viscosity, flux density, and so on. So there are a lot of input that we need to consider for the casting, and also the workers. Okay, workers. So there are 3 workers here, and the supplier are related with the input here, the material supplier, the supplier of the mold, the supplier of the furnace, and so on. Right, so in a SIPOC diagram, the main things that we want to have or to get is the input. Okay, then for the deburring, so the input are casting product, so means that after casting, so the casting part will be sent to the deburring department, then deburring machine, then the workers who operate the machine, the grain materials, okay, the material that we use in the deburring process, then the input material, okay, maybe the speed of the deburring machine, the grain size, duration of the process, and so on. Okay, then for the turning, so we have a lot of input from the turning. Then for the milling also, we have a lot of input from the milling. Okay, so the input for turning, for example, the machine itself, the insert material, dimension, parameters that be used, coolant, workers. Then for milling, we have cutting tool, clamp, tool size, tool type, spindle, feed rate, depth of cut, coolant type, workers, and so on. So these all are the input for particular process. Right, so next we want to identify the critical process that contribute to the surface finish. Okay, so based on the input from the expert in the process, okay, there are 2 main process that contributed to the surface finish. Okay, the turning process and the milling process. So for the next analysis, we only consider these 2 process. Okay. Okay. Next, we will fill in the cause and effect matrix. So this is the template for cause and effect matrix, right? So first of all, we need to fill in the output. Okay. So the output here is taken from the CTQ drill down at the indicators place. So these are the output that we will put inside the cause and effect template. So these are the output. Right, so now we will list down all the output. Number 1 is the glossiness, then wavelength, then the roughness, surface roughness, skewness, kurtosis, Number 6 is a rating, the rating of the customers regarding the aesthetics. Then number 7 are the then. Okay, so these are the output that we taken from CTQ drill down indicators, and we transfer into cause and effect matrix. Next, we give or prioritize the output here based on the customer. So based on the importance to customer, which one are the most important? Okay, so the most important output will be given scale 10, and the output that not important to the customer will be given scale 1. Okay, so in between there we can give the rank based on the importance. Okay, for example, for the glossiness, okay, glossiness between scale 1 to 10, maybe this one is 5. Okay, the wavelength is 7. The roughness, okay, maybe this is the most critical one, so 10. Okay, the skewness maybe 5. This one courtesies maybe 6. The rating maybe 8, and the dance also maybe 8. Right, so we already give the importance. So again, for the rating here, importance to customer, we can conduct or we can do the brainstorming in order to identify the importance of the output to the customer. Okay, next we will fill in the input variable and the process here. So the input variable and the process based on the SciPop. Okay, based on the SciPop, which previously we already shortlist two process that contribute to the surface roughness are turning and milling. In the case that we didn't have any ideas which process is actually contributed to the problem that we studied, we also can take all the process and all the inputs and transfer them into the cause and effect matrix. Okay, so in this case, we only concentrate on turning and milling. So for turning and milling, so we will fill inside the process here. Okay, the process is milling. Then input variable is a tool type, maybe. Okay, so we fill in the form here. Okay, now we already fill in the form. Okay, in terms of the glossiness, in terms of the output and also the inputs that we consider. So for the process, only two process that being shortlisted, milling and turning. So the input variable for millings is being put here, and input variable for turning, okay, will being put here. So next we need to give a rating or the ranking. Okay, is there any relationship between the input variable and the output here? Okay, again, for this one, we will give the rating between 1 to 10. 1 means that there is a least relation. Okay, 0 is no relation at all between the input and the output. Okay, 1 is a very least relation, and 10 we have a strong relation between the input and the output. Okay, for example, between tool type and glossiness, okay, maybe it's not have much relation, so maybe we can put 2 here. Then tool type and wavelength, okay, 5. So again, in order to give the rating here, we need to make a brainstorming and the involvement of the expert in particular process or particular service that we studied is very important here. Okay, tool type, roughness, let's say 7. skewness maybe 1, kurtosis to tool type maybe 2, rating maybe 4, here is maybe 7, and so on. So from here basically we need to we call give the rating for all of the process. Okay, now once we have put all the rating, okay, so the template here will automatically calculate the total score. The total score is basically the multiplication of the rating between input and the output, then multiply with the importance to customer. For example, the first term here, E8. E8 is referring to this number, multiply with the importance to customer here. Okay, so basically is the score here is basically the summation. We multiply the rating here with the importance to customer plus with the rating on this one, multiply with the importance to customer, and so on. So we already get the total score, right? We already obtained the total score. So now next what we need to do is to sort the process and input variables here according to the score, okay, in descending order, right? So we select the process until the total score, then we sort it, okay, sort by O. O is the total score from largest to smallest, okay, right? So we already get the rating, overall rating here, from the largest to the lowest. Okay, so next what we can do to proceed with the next step is we want to shortlist the input variable. So as been taught in lecture, we have a few approach. So we can directly select 4 to 5 top process or top input, or we also can utilize 20% score, okay, or top quartile of the score, right? If we use a top quartile of the score, so we need to calculate. Okay, so right now the maximum score is 389. So top quartile will be 25% of the score. So we try to calculate first. This one multiply with 25%, right? So one quartile is equivalent to 97. Okay, so this is the quartile. Okay, and top quartile will be the maximum score minus this number. Okay, right, so 291.75. So means that if we utilize the top score or the top quartile approach, so any input that above 291 will be chosen. So if we refer to the total score here, okay, so these 5 inputs are the input that above the top quartile. So means that we will proceed with these 5 input, okay, for our further analysis. So we have milling, 3 millings, yes, spindle speed, depth of cut, feed rate, then turning, cooling temperature, and insert size. Okay, so we need to proceed with these 5 input for the FMEA. Okay, now we will proceed our analysis with failure mode effect analysis, or FMEA. So this is the FMEA template. Okay, so now we are for the process of product name, so now we are considering the surface roughness. Okay, surface roughness. Okay, so you need to fill in the responsible person or PIC person. Then this FMEA is prepared by whom, then the date, the original date and revision date. So this is the template of FMEA, right? So basically, for to begin the FMEA, normally we will fill in the process, key input, potential failure effects, potential causes, current causes, until the RPN. Then the recommended action, responsibility, action taken, and so on. This part will be filled in when the main one has been completed. So means that we will focus on this part only. Okay, for this example. Okay. So basically, for the action, responsible action taken, and so on, will be filled in once we conduct the action to improve the failure. Right. So what we will do here, we will transfer the information from the cause and effect, okay, especially on the process and also the inputs, the critical input that we already chosen from a cause and effect here into FMEA. So now the process step, okay, the first process that we consider here, taken from the cause and effect, is the milling. Okay, milling process. Then we'll enlarge this part. Okay, the milling process. So what is the key process input? Okay, so key process input has been identified earlier in cause and effect. The first one is the spindle speed. Okay, what potential failure mode? What will be the potential failure of the spindle speed in the milling? In what way does the key input will go wrong? Okay, what is possible failure for the spindle speed in milling process? Okay, for example, it might be too fast. Okay, so if too fast, it will damage the tools. Okay, so this is the milling process. Okay, what else? Then for the spindle speed also, it might be too slow. Okay, it might be too slow. Okay, so this is also spindle speed. It might be too slow. So what happens if the spindle speed is too slow? So maybe it will damage the surface. Okay, this one maybe it will damage the surface. Okay, next. Potential failure effect. What will be the potential failure effect of the process? Okay, so maybe here it will damage tool, maybe the surface will burn, okay, because of too fast. Then it might also, when we use a high spindle speed, maybe it requires the high energy, okay, high energy in cutting. Then how severe is the effect to the customer? How severe effect to the customer? Again, for the severity here, we will put the rank between 1 to 10. Okay, maybe for this one is 8. Okay, Then the potential causes of the problem. What will be the potential causes of spindle speed become too fast? So maybe a wrong setting. Then maybe the controller failure. What else? Maybe because of unstable power supply. Okay. Then occurrence. How often does the problem occur, or the frequency of the problem? Okay, again we need to put the rank between 1 to 8. So maybe here is also 8. Okay. So what are the current control? Okay, so include the SOP. So the current control, or the current control to avoid this problem. Okay, so maybe at the moment we don't have any current control, so no current control plan. Then detection, how well you can detect the cause or the problem. Okay, so maybe here is 5. Okay, right. So the template will calculate RPN directly based on the rating that we give. Right, next is spindle speed too slow. So the problem that might occur here is damaged surface, for example. Okay, so means that the surface of the part is damaged. Then what else? Low production, okay, because of uh, spindle speed, so it will reduce, or will reduce the production. Then it might also cause a dull surface, for example. Okay, so again we give the ratings. So maybe here is 5. So potential causes, maybe the wrong. Okay, just I think that's the same with the burst wrong setting. Then maybe the controller failure, and so on. Okay, so maybe these are the potential causes. Then the occurrence maybe 3. So current control, just to monitor, just manually monitor the problem. Then detection, maybe 5, for example. So it will come out with the RPN. Okay, so we try to list all of the problem or the process step and key process. Okay, the first one is spindle speed, then maybe in terms of depth of cut. So again, this is under milling, and this is also under milling. So for the depth of cut, what are the possible problem? So maybe overcut, and there is also will be undercut. Okay. So what will be the potential failure of undercut, overcut? So for overcut, rough surface, it will make the rough surface. What else? Wrong machine. Okay, it also might cause the tool to break. Okay, so we need to fill in all of the potential failure, potential causes, and so on for all the problems that we face. Okay, now we already complete to fill in the FMEA table. Okay, again for process step, key input process, failure mode, and so on. Right, so we already fill in the milling, which consists of spindle speed, depth of cut, feed rate, then for the turning, about the cooling temperature, and also the insert size. So again, this input is taken from the cause and effect table, okay, from the cause and effect table. Right, so once we already fill in all the required information in the table, we also have the RPN number. Okay, so again, the RPN number is coming from the multiplication of severity, occurrence, and detection. Okay, so this is the RPN number. And once we already complete to fill in the table, the next step is to sort the table. Okay, the same process as we did in cause and effect diagram. So we sort the table in the descending order, meaning from the largest to the lowest. Column J, from the largest to the smallest. Okay, right, so now we already sort the RPN, and again during this step we could utilize a few approach. Either we want to use the Pareto approach, which means that we choose 20% of the top input, or we could use the quartile approach. Okay, top quartile approach. So based on the RPN number, the highest score, okay, the highest score is 320. Okay, so the quartile, okay, quartile is 25% of the highest score, and the top quartile will be the highest score minus quartile, so 240. So means that any input that have the score above 240 will be chosen for the following stage. So in this example, so these are the top input that we will bring to the following stage. Okay, so so in this example, so we will choose the milling, okay, which refer to spindle speed, then milling depth of cut, then milling feed rate, and finally the turning process coolant temperature. Okay, so now we already finalized the input that will be utilized in the analysis phase or analyze phase. All right, since our coverage or our syllabus for introductory Six Sigma is only up to measure phase, so basically this is the last step in the measure phase. All right, so means that we already identify a few relevant or related input that we need to further investigate in the analyze phase. And again, at this point, these input are only based on our assumption. Means that we only assume this input will have the effect on the surface roughness. Okay, so in analyze phase, we will validate, is it true that this input is having the significant effect on the surface roughness or not. So means until or up to the measure phase, we only shortlist a few relevant indicators or few relevant inputs to be further analyzed in analyze phase. So that's all. Thank you.